In this lesson, we will discuss the engines and APU system overview. The airplane is powered by two General Electric GE Next 1B67 engines. The engines are rated at 67,000 pounds, B787-8, 74,100 pounds, 787-9 of takeoff thrust each. The GE Next engine is a high bypass, two-shaft axial flow turbofan engine. The engine has primary core airflow and secondary bypass airflow. The bypass ratio of this engine is approximately 9.2 to 1. This means that 9.2 times more secondary air goes through the engine than primary air. For the 787, no external engine air bleeds are taken for aircraft systems, and as a result, this maintains high internal engine pressure ratios, which in turn improve the specific fuel consumption, the SFC. The engine is a two-rotor axial flow turbofan engine of high compression and bypass ratio. The N1 rotor consists of a fan, a low-pressure compressor section, and low-pressure turbine section on a common shaft. The N2 rotor consists of a high-pressure compressor section and a high-pressure turbine section on a common shaft. The N1 and N2 rotors are mechanically independent. The three cowls, or cowl pairs, provide a smooth aerodynamic airflow over, through, and around the engine. The inlet cowl, thrust reverser halves, the exhaust cowl. The inlet cowl makes sure the correct and smooth airflow goes into the engine for all aircraft speeds, attitudes, and throttle settings. It also aerodynamically smoothens the airflow around the nacelle. There are 18 wide-chord fan blades. The fan blades are made of carbon fiber reinforced plastic, CFRP. The leading and trailing edges are titanium. This protects the blades from FOD damage. The 787 engine compressor section has a single-stage fan, 4-stage booster low-pressure compressor, and 10-stage high-pressure compressor. For the 10-stage high-pressure compressor, the stages 1, 2, and 5 are blisks. The stages 3 and 4 and 6 through 10 are individually bladed spools. The inlet guide vanes and stages 1 through 4 have variable stator vanes, VSVs. The combustion chamber controls and mixes the compressed air and fuel for combustion. It is an annular-type combustor with inner and outer liners. It has a cooling airflow into and around the unit. High-pressure turbine is a two-stage turbine. It changes the energy of the hot gases into mechanical energy. The high-pressure turbine uses this mechanical energy to turn the high-pressure compressor rotor and the accessory drive. The low-pressure turbine has 7 stages. It turns the fan booster rotor with the low-pressure inner shaft. The low-pressure turbine has active clearance control to optimize blade tip to shroud clearances. The high-pressure rotor turns counterclockwise. The low-pressure rotor turns clockwise. The turbine exhaust system is an exit duct for the turbine exhaust gases. During usual engine operation with the thrust reverser stowed, the exhaust gas is contained and goes out through the exhaust components. The exhaust nozzle controls the airflow of the turbine exhaust as it leaves the combustor section. It also makes the outer contour of the exhaust gas. The engine-driven accessories operate by a gear train attached to the engine core. The N2 shaft drives the gear train. The accessory drive system has the transfer gearbox and the accessory gearbox. These accessory components are on the accessory gearbox, the variable frequency starter generators, engine-driven pump, main fuel pump, permanent magnet alternator, lube and scavenge pump, main fuel and oil heat exchanger, metering unit, main fuel filter, flow split valve, fuel adapter, N2 speed sensor. The engine fuel feed system supplies fuel from the main and center fuel tanks. Fuel from the tanks goes through the main fuel supply hose to the engine main fuel pump, MFP. A centrifugal boost element in the pump pressurizes the fuel through the nozzles into the combustor chamber. The main function of the engine fuel and control system is to control the fuel to the combustion chambers in response to commanded power. The engine fuel and control system is a full authority digital electronic control system. The Electronic Engine Control, EEC, is the central component of the FADEC system. It controls the operation, performance, and efficiency characteristics of the engine through the subsystems. This is a two-channel computer system. The EEC electrical harness is the connection between the engine sensors, actuators, engine control electronics, and the airplane. The permanent magnet alternator, PMA, provides the primary source of electrical power for the EEC when the engine is running. The PS3 sensing supplies the static discharge pressure of the compressor air to the EEC for these engine control algorithms: maximum engine pressure, idle speed, lubrication system sump pressurizations, stall protection, combustor flame out margins, auto relight schedule, engine anti-ice. The T12 sensor supplies the fan inlet air temperature data to the electronic engine control, the EEC. The EEC uses the T12 sensor as backup to the airplane total air temperature, TAT. T25 sensor. The T25 sensor senses the temperature between the fan and high-pressure compressor, HPC. The sensor data is used to calculate the corrected core speed. The EEC uses this for engine control. The T3 sensor senses the temperature of the high-pressure compressor discharge airflow. It is used for fuel scheduling and active clearance control. The engine thrust control module is the control interface between the pilot and the engine. When the thrust lever moves, it turns the throttle lever angle resolver. The resolvers send thrust lever resolver angle data to the EECs and the Common Core System for thrust control. The thrust management function supplies automatic thrust command signals to the EEC with the auto throttle servo motor. It turns the throttle level angle resolver and thrust lever.